All right, one of the other applications we're going to look at in section 6 is compound interest. So compound interest is when you are put in an investment into some account that is going to pay you interest. So interest is just money that you are earning, in our case, or paid in other cases, to yourself or on something that's money you have borrowed. So in general, we're going to think of compound interest as you're making money. So compound interest can be simply found by this formula. A equals P, 1 plus R over N to the NT. Making sure we remember this exponent is kind of, both of those things are in the exponent. That will become an issue when you start putting them in the calculator. So if we look at this, we have A equals P, 1 plus R over N to the NT. There are 5 variables, so we'd like to kind of know what those variables stand for. So A is going to be the amount that we have after T years. So after this money's been sitting in an account for so long, how much do you have in there? P is what's called the principal. So the principal basically is just the starting amount. How much do you start when you start your investment? R is, of course, our rate. Now, for a rate, we generally want to put this in as a decimal. So if it's 10%, you want to go with the 0.10. If it's 8%, 0.08, things like that. N is the one that's kind of different because T is, of course, just time, and that's the number of years. Now, the only thing I'd mention about that, if it's, say, 6 months, then 6 months could be half a year. Now, N is a little different. N is the number of times compounded. Now, what that means, number of times compounded, is basically how often do you earn interest. So do you earn interest every month, every day, twice a year, every quarter? So that is what this N is. It's how many times are you making interest. Because you can get interest more often and just get smaller amounts of interest, or you can get it less often and get bigger interest each of those times. Now, putting them together, they work out pretty close to be the same. There is a limiting factor, as we will see, that is dealt with our letter E, or our number E, I should say. So we'll look at some examples of how we do this. We're really just plugging into this formula. In the next section, we'll actually work backwards and try to figure out how long some of this stuff takes. So this says Dave invests $300 in an account with a 5% interest rate. If he makes no other deposits or withdrawals, find his account balance after 15 years if interest is compounded with the following frequency: semi-annually or monthly. So our principal in this case, what we start with $300, so that's going to be my principal. My rate is 5%, so I'm going to write it as 0.05. The other things I know is I know that after 15 years is going to be my time, and then my N is going to change in these two problems. For example, semi-annually means I get interest twice a year. So my N is 2. It's just the number of times you're getting interest every year. Monthly, obviously, N will become 12, so I get interest 12 times a year. And so even though I'm making it 10 more times, I think you'll see the amount you make is not that much more. So for this one, my A is equal the principal, which is 300, 1 plus the rate, which is 0.05 or 0.05, divided by 2, to the power. Now, what I do, I'm going to do N times T, which is 2 times 30. I like to go ahead and put those in their own little separate set of parentheses. That will kind of alleviate any issues you might have with putting the wrong parenthesis or things like that, getting the wrong value. So if I put all this into a calculator, and I would certainly pause this video and make sure you get the same thing I'm getting $629.27. So if I put $300 in an account and wait 15 years, it grows to $629.27. Now the question is it worth you losing this $300 for 15 years to make another extra $329? Now monthly, the only thing that would change it would be 300, 1 plus 0.05. Now instead of 2, it would be 12. And it would also be 12 up here because it's NT up there. Sorry, that is not 30, that is 15. I was multiplying those together. Same thing up above. I think I typed in the calculator right. I put this wrong though. It's 2 times 15 because it's 15 years. My apologies. 2 times 15 is 30. That's why I put 30. But I did put it right in the calculator. So if I put this in the calculator, I'm getting 634.11. So it is more interest, but not very much more. It's like $5 more. So if I get interest, 12 times versus 2 times, I'm only getting like $5 more interest. So it's more, but not a ton more. So let's look at another question. This says, when Amelia turned 6, her grandparents opened a college savings account with an initial deposit of $500. So that sounds like my principal. The account earns 3.2% interest, so that's 0.032, compounded bi-monthly. Bi-monthly means every other month. So if I'm doing it every other month, I'm getting it 6 times per year. So I get the first 2 months, second 2 months, third 2 months, fourth 2 months, so on and so forth. And it says, if her grandparents make no other deposits or withdrawals, how much money will be in the account when she can get to it at age 18? So our time, well, she is 6. So when she's 18, that will be 12 years. So that is our value in this case. Okay, so we have P of 500, R of 0.032, N of 6, and T of 12. So if I put this in, I'm going to get 500 times 1 plus 0.032 over 6 to the power 6 times 12. So if I work this out, I'm getting $733.32. So that $500 in 12 years is made of an extra 200-ish bucks, $233. So that would be how much she could pull out of this account when she is 18. All right, so let's look at another example. Suppose a savings account offers a 4% interest rate compounded semi-annually. If Samantha opens an account with $750 and makes no other deposits or withdrawals, how much interest will she have earned after 10 years? So this one is slightly different. It's still compound interest, so it's still A equals P, 1 plus R over N to the NT. So we're going to start with a principal of $750, so that's fine. We're going to have a rate of 0.04%, so that's 0.004. Remember, we have to move it over 2 spaces. And it's compounded semi-annually for 10 years, so our time is 10. Now, semi-annual basically means 2 times a year, so N is 2. So why this is a little different, we can certainly plug in like we always have, 750, 1 plus 0.004 over 2 to the NT, which is 2 times 10. And I would encourage you to put this in the calculator, make sure you're getting the same number as me. So I am going to end up with $780.58. Now, unfortunately, in this problem, that would be the incorrect answer because it wants to know how much interest has she made. So how much extra money has she made? So to find the extra, we'll have to take our $780.58 and subtract what I put in. That's going to tell me how much money I've made in those 10 years. So in this case, I've only made $30.58 in 10 years. So not a lot of interest. And the reason for this, obviously, is we have such a small interest rate. 0.4% is very, very small. That's going to not earn interest very quickly. All right, let's go ahead and look at one other kind of interest-bearing problem, kind of similar to our growth and decay. We had our normal growth and decay, and then we have what was called continuous growth and decay. So continuous growth and decay is when you are making interest constantly. But the problem is, since you're making interest constantly, the amount of interest you make is very, very small. So you're making a very, very little bit, but you're making it all the time. So the formula for compound interest is A equals P e to the RT. And everything else kind of means what it has in the past. So A is the amount in your account after T years. P is going to be your principal. R is your rate. And T is your time in years. And then E is that special number that we've seen. It's just some number that, the calculator knows. It's that magic constant. So we have P, and we'd have R, and we'd have T. We don't have the N in this case because N is basically infinite. We're doing this over and over and over again. So if we look at this example, it says suppose $800 is invested at 6% interest rate compounded continuously. So when you're doing mixed up problems, you want to make sure you look where it says continuously, because that's going to be a different formula versus whether it said quarterly or semi-annually or whatever that might be. So that's going to be A equals P e to the RT. So our P, how much we start with, is $800. Our rate is 6% or 0.06, and our T is 20. So I'll simply just plug those in, and I would encourage you to do the same. Pause the video, make sure that you're getting the same value I am. So 800e to the 0.06 times 20. And again, these parentheses around the exponent will really make sure that you're getting the correct answer. So I am getting $2,656.09. So we've almost tripled our money in 20 years, which is pretty good. And it's really not the continuous nature that's making us get so much money. It really is the interest rate. So the interest rate in this one is 6 versus our previous one, which was like a 0.4%. The better interest rate is going to really drive how much money you're getting. All right, let's look at one last example that'll kind of see if you had a decision to make, if you had two accounts to pick from, which one would you pick? So let's say that Carla is investing $1,500 in a new 30-year retirement account. So $1,500 in a 30-year account. And we have two choices to pick from. You can have an interest rate of 5.5 annual interest rate compounded monthly. So you get 5.5% interest. You only get it monthly. Or 2.7%, so a much lower rate, but it's compounded continuously. So the question is it better to have a higher rate and not get interest as often, or a lower rate and get interest all the time? So if you look at A is going to be our traditional kind of compound interest problem. P, 1 plus R over N to the NT. This is the one we'll use for option A. Now option B is continuous, so that's going to be the other one we have. That's A equals PE to the RT. So we'll just plug numbers in these. So for option A, for both I'm going to invest $1,500. 1 plus, now the rate for the first one is 5.5, so 0.055. And compounded monthly, that's 12 times a year, to the power 12 times 30. So for continuous, similar, we're going to start with 1,500 e to the 0.055 times 30. And again, I want to make sure I put that exponent in parentheses. So go ahead and pause the video, see if you can't figure out what these are, and then we'll see which one is a better option. So option A, I am getting $7,781.08. Option B, I'm getting $3,371.86. So even though I'm getting interest constantly and continuously, because it's a smaller rate, you can see it's a lot less money. So option A is by far the better choice because you're making nearly $4,400 more. So even though you're only getting interest every month, it works out better because that rate, interest rate, is always the factor that's going to drive how investing in compound interest always works. So, hopefully this is helpful. In section 6, we'll actually try to figure out how long things take as we finish up our exponential unit.